So this is a supplemental chapter that we're doing now. We've finished chapter 5, and that's really everything out of our textbook that we're going to cover. So we've got 2 more topics that I want to cover, and I'll get through both of them if time, if not at least logistic regression. The second one is survival analysis, which actuaries use to some extent. And we do a fair treatment of survival analysis in MA345, which some of you had last semester, last spring. And we talked about survival distributions. Well, this is how you statistically analyze survival distributions. So I'd like to get to that if we have time. But even more important is the topic of logistic regression. So logistic regression deals with regression models when your y variable is dichotomous. What does dichotomous mean? Right, two levels, right? Or also referred to as binary data, right? So for binary data, and a lot of times it's a yes-no variable. So you do a survey and you ask a question, yes, no, and then you try to model, you try to predict the probability somebody will say yes based on their personal characteristics of some kind. So you have all these X variables. Or it might be, what's the probability somebody takes out a life insurance policy? What's the probability they submit a claim, right? During a year, they either submit a claim or they don't. That's binary data. Now you can try to predict the probability of that using a regression model, right? Well, the problem is when your y variable is dichotomous, we'll set that up as a dummy variable. So y will equal 0 if no, and 1 if yes. Whatever it is that you're counting, right? So we call yeses successes and nos failures. So you're trying to model the probability of a yes and a no. Well, clearly, this is not going to satisfy the normality assumption, right? The y variable should be normally distributed. It's binary. It's not going to satisfy a normal distribution. So you can't really fit a regression model to predict y. Think, well, instead of predicting y, let's predict the probability of y, right? So the probability of y, put it inside the parentheses, probability that y is a 1, right? Predict that with some function. And that is possible, but it still doesn't work very well. It works a lot better than just putting y there as a linear function of a bunch of x's. Put the probability of y instead, it works a little bit better. Now instead of 0, 1, you got a number anywhere between 0 and 1, right, for probability. But it still doesn't work real well. So what we do is we convert probability into odds, and then we model the log of those odds. And that works pretty well, right? So let me illustrate this. I think I've already posted. If not, I will post soon this document, which I just found on somebody's website. I don't have a copy of a book to give you for logistic regression. For copyright rules, I can't just Xerox the chapter out of a book. But if it's out on the web, it's fair game. I found this. It's okay. It's not great, but you'll be able to get by just on what notes I give you. So I'll post this out there. This first page is pretty much what I just said, but the example that they're going through is regression of sex on height. So it's kind of a contrived example where they're saying, I wonder if I could tell, just by knowing somebody's height, can I predict whether that person was a male or a female? Right? And so this curve that's going up through there, this is P for probability. The probability gets stronger that it's This is percent that's female. Height in inches, as you go up in inches, you've got very few that are female, but by the time you get to the mean height for females, which is about 65 inches, you're up to about p equal 0.5, and then it tails off. So by the time you get up to a high probability, or I'm sorry, a tall height, you've gotten almost all the females there are. Right? So this is a cumulative distribution of female height. Right? So then the question is, can I model, if I know their height, can I model what the probability is of being female? Right? Well, like I said, it doesn't work very real well to model probability straight. So we fit what's called the logistic curve. Right? So first, let's talk about the relationship between probability and odds. Now, you gamblers all know what odds are, right? So the odds of y equal, I'll say yi, so a particular individual. The odds that a particular individual is a 1, instead of the probability they are a 1. How does that relate to probability?
Well, it's 1 over a finite number, isn't it? Or a discrete number?
Well, but just, yeah, it is, but how do you compute odds from probability?
1 over the probability.
What's that?
Isn't it 1 over probability?
No, it's not 1 over the probability.
Isn't it the number, let me see here, the number of successes versus the number of failures?
Yes, that's exactly right. So let me go the other way. I'll give you odds and see if you figure out the probability. The odds of this horse winning are 3 to 2. 3 to 2 odds. 60% chance. So you get it instantly going the other way. So what do? You say, okay, I've got
5 total.
I got 5 total. I've got 3 out of 5 are winning, and 2 out of 5 are losing, right? So the 3 out of 5. So the odds is computed from probability as probability over 1 minus probability. So if probability is 60%, that's 0.6 over 0.4, which is 3 to 2 odds. Right? So it's easy to get from one to the other. Now, what probabilities are limited to be between 0 and 1? What about odds? Can't be below 0. They can't be negative, right?
Can't be 0 or the problem.
Yeah, it can be 0.
Yeah. No.
Because if the probability is 0, then the odds are 0, right?
I'm in.
But what if the probability is really, really close to 1?
That's what I said.
It will explode, so there is no upper limit. It will approach infinity. As the probability approaches 1, 1 minus something really close to 1 is really close to 0. When you divide, it will make this thing explode, right? So instead of being limited between 0 and 1, odds are limited between 0 and infinity. So it works a little better for regression. Well, the problem is that it's a very curved relationship. So fitting a linear regression to that doesn't work very well either. So what we do is we take the log of the odds. So if this represents odds, and this is log of odds, that's just your normal log function, right? And the odds, if the odds get close to 0, what happens to the log of the odds? They shoot down towards negative infinity, right? So the log of odds can go from negative infinity to infinity. You get back the whole range. But it's generally this part of the curve that we're interested in. And after you get out here very far, that thing is pretty linear. So it works pretty good to fit linear regression to the log of the odds. So we fit log odds, which is called the logit transformation. Right? So you convert from probability into odds, then you take the log of the odds and you got the logit function. So the type of regression is called logistic regression. Okay? So I scrolled past it, but a minute ago you saw an equation in here called the logistic curve. Right? So if you exponentiate log odds, then you get the exponential of a log is that thing back, right? You get the odds back, and then you got odds over 1 plus odds. That's probability. Okay, that's this function. If I reverse this, I'll just call this O. I've got O equal P over 1 minus P solved for P. Okay, I can do that because I'm good at algebra. O times 1 minus P equals P. O minus OP equals P. And O equals P plus OP. Factor out. What am I solving for? P. Yeah. For a minute I thought, oh, I'm solving for O. I'm going backwards. Solve for P. You factor out a P. And you got 1 plus O times P. Divide through by the 1 plus O. And you get this. 1 plus odds on the bottom. Right? So this, if I take the log odds, and we'll use natural log, the log odds is equal to some linear function of x's if I exponentiate both sides of this, I get odds back, right? Exponentiate the natural log and you get odds, you get the thing back, so we would get odds back. So odds would be equal to e to the linear function power. So that's what you're seeing here. So odds over 1 plus odds gives you probability. So the idea is we do the logit transformation, then we model that log odds as a linear regression. And all the things we've been doing with linear regression work here, right? Well, no, I shouldn't say it. It's not true. They don't all work, but it works similarly. The problem is that this is called a nonlinear regression because this side is all log and odds and all that stuff. And so least squares estimation doesn't work. So what we use here is maximum likelihood estimation. Now, who's had 345? No, that's 343. So, yeah. It's MathStat 2. You guys had MathStat 1. And we might have... did we talk about maximum likelihood estimation? If we...
Is that ranking them from like Y1 to Y whatever and you're trying to figure out?
Kind of like that, but you'll learn it in MA345, maximum likelihood estimation, which is MathStat 2. But in a nutshell, likelihood function is very closely related to probability density function, only it reverses the role between the random variables and the parameters, right? So if you have a normally distributed random variable x, then you have a function, a density function, that gives you probabilities, right? And that density function will be a function of the x plus mu and sigma. Those are the parameters of a normal distribution. Well, now we treat those parameters as if they were the variables and the x's as if they were the fixed quantities, right? And that's called a likelihood function. So you want to know what values of the parameters maximize the likelihood of getting the data I just observed. Those are called maximum likelihood estimators.
Is it always unbiased?
Not always. Maximum likelihood estimators are not necessarily unbiased. So, and that's part of 345 also, is that you come up with an idea for an estimator, then you check to see if it's unbiased or not, and then you try to find, among all the unbiased ones, you try to find the one that has minimum variance. Right? Remember all that? But we don't have to talk about that here. Right? So, let's take a real simple example here and fit a logistic regression model, one that you can actually do by hand from a 2x2 table. Right? So I have a response variable at 2 levels, yes, no, and I have an x variable at 2 levels. So it's a categorical x variable and only has 2 levels. There's nothing about this that says x has to be restricted like that. That's just the simplest case. X can be a continuous variable, or these x's can be dummy variables for some categorical variable. So you might have race as a predictor for whether or not somebody takes out an insurance policy. And then you have 6 races, and you make a dummy variable for 5 of those 6, just like we've been doing. Right? So these x's can be anything. But let's take a real simple example. This is from the MEPS data, which is your project. This is the MEPS data that was used in an old textbook, so it's much, much abbreviated. The actual MEPS data has, I don't know, 800,000 records or 1 million records or something, and this is like a random sample of 20,000 of them or something. So it's still a huge data set, but the one I'm using is even much smaller than that. But that data step up there is, you don't have to understand what that code is doing, but it's just setting up data that I get combination between a variable called sex and a variable called hospital, and then counts. Right? So it's going to form a 2x2 table, which I'll run this proc freak to show you that table. So what we're trying to do here is predict being hospitalized. So that's the hosp variable. Okay? So being hospitalized based on gender. So I run that, and I get this proc freak output. So it's a contingency table. So my 2 groups are gender, and now I don't. Did it say which was which? 0 or 1 was male or female? Usually males are 0s, but
the number of X chromosomes we have.
yeah. I can actually figure it out by looking at the numbers because I know what the numbers are. This is hospital. This little thing says frequency is in the top. Then percent is the next one down, and that's percent of the grand total. So we've got 2,000 grand total. And then row percent, column percent. So the row percent. So whatever 0, hospital 1 is yes. So 4.65% of this group got hospitalized. And 10.7% of the other group got hospitalized. So which one are females? Females get hospitalized more than males. And that's just the truth. Right? It's a lot of it's due to children and complications with childbirth. What'd you say?
I'm not so stubborn.
And that's it also. Yeah. Males are much less likely to go to the hospital when they should than a female is. So females tend to get hospitalized more than males. So we know from that the 1 is females. Okay? I just realized I forgot to bring my notebook down here with my notes in it. I may have to run upstairs because I don't know if I have all this memorized. But let me see if I can do it. I'm going to copy this table down because that's kind of hard to read. But I'm going to copy it over here. We've got sex 0, 1, and then we've got hospitalized and 0, 1, like this. Okay, and then we have a total, column or row totals and column totals. And so we've got 902 and 44, and then 941 and 113. And the totals are 946, 1054, for a grand total of 2,000. And then
1843 and
157. Okay?
So did you reduce it down to 2,000?
Yes.
Or was that, okay.
I think the old textbook, I think they went down to 2,000. I said 20,000 a minute ago, but I think it was 2,000. Right? So I'm going to turn off the projector, and we're going to do this by hand. And then we're going to run it in SAS and show how to get those results. Okay, so think about this. Right? First of all, what is the probability of hospitalization? I'm just going to use H. Probability of hospitalization given a male. I'll use an M. So these are male and female. Right? So probability of hospitalization given a male. What's that probability? 44 out of 946. And that was those row percentages we were looking at a minute ago. But 44 out of 946, give me that as a decimal.
0.0465.
0.0465. Okay? Now do the same thing for females. Probability of hospitalization given females. 113 out of 1,054. 0.1072. Okay? So what are the odds for males? Not 1 over.
Oh, yeah, I'm sorry.
0.0465 over 1 minus 0.0465. 4.877. Okay? And the odds for females?
I told you percent, you want the decimal.
What's that?
Times 500, you want the decimal.
Oh, yeah, I want the decimal.
0.0487.
Okay, I should have caught that couldn't be right, just looking at it. When probability is close to 0, the odds and the probability are very similar. So this number should be almost the same as that number. When you get further away from 0, then the odds take off. So what is it for females? 0.1072 over 1 minus 0.1072. Come on. I can't do it in my head. What? 0.1201. Give me one more place.
Okay, 12007.
007. Okay, that'd be good enough. Okay? Now, remember, we're modeling log odds, not odds. So I need to take the log of those values. But let's write out that model. The log odds of hospitalization, I'll go ahead and write that, is equal to beta 0 plus beta 1 and I'll just write out the word sex. Right? It's an X variable, but it's a dummy variable for sex.
So it doesn't matter if we do the natural log or any other log. log.
It technically does not matter, but always use natural log. Right? All of the formulas and functions are given in terms of natural log and base E exponentiation. Okay? So let's come over here and do log odds. Give me the natural log of these. Log odds for males.
It's negative 3.0207.
Okay. And the log odds for females?
It's negative 2.1197.
1197. Okay, everybody getting that? Well, now I need to figure out what these betas would be to give me those values. When sex is a 0, we're talking about males. So my males is the reference group, right? So for males, the log odds is equal to beta 0 plus 0. So log odds for males, I have a value for that. That must be my beta 0, or my B0, my estimate of beta 0, right? So B0 is log odds for males, which is negative 3.0207. Now, find B1. Well, if I do females, the log odds, which I have a value for over there, is equal to B0, which I already know now. All right, so B0 is negative 3.0207 plus B1 times 1. I need to know what B1 is. Where'd the 1 come from? I'm plugging in a 1 for the sex variable because females had a value of 1. So I'm just taking B instead of beta because it's an estimate times 1. All right? Solve this for B1. Okay? And it is, I'm going to go ahead and write it out, but negative 2.1197. And then I'm going to add this to both sides since it's negative. Right? Add that over. So plus 3.0207. And what'd you say it gives?
0.90102.
90102. So now, what's my model? My fitted model to this data is, log odds, and not specifying gender, because that's in the model, is negative 3.0207 plus 0.90102 times sex. Right?
So in the model statement, you still do, you don't put like Y having when you do these?
Actually, this should have a hat on it. The estimated log odds from this data. Right? So you're right. The one thing that's missing from here, and I forgot to mention it before, there's no error term. There is no error term in logistic regression like you're used to. Right? An error term in linear regression represents residual. What's the residual? Well, here we don't have a residual because our y variable is only 0, 1. Right? And instead of estimating the value of that y variable, we're estimating the log of the odds of that y variable occurring. And so there's no residual associated with that. So we don't have an error term in a logistic regression model, which gets confusing. But question?
So if you want to find the probability of it being a male, you can just plug in a 0 and put like put E on both sides, and then convert it to.
Well, it's not the. Yeah, it's not the probability of being male. It's the probability of being hospitalized if you're male.
Yeah.
Yeah. Okay.
So you can use that to find probability.
That's right. So let's do that. All right. What is the probability of being hospitalized given male from this model? Well, I don't know, but I can do log odds, right? So what are my log odds for being male? The exponent, because this term's 0, right? I'm not exponent, the intercept, because this term's 0. So the probability, the log odds, are negative 3.20, I'm sorry, 0207. Right? And then the odds, e to that power. So odds equal e to the negative 3.0207 power. And then get from odds to probability, e to the negative 3.0207 over 1 plus e to the negative 3.0207. Do that on your calculator. 0.0465. 0.0465. Right?
When I did that, it gave me 0.04877. What should I get the odds? Then after you convert it back over to probability, you get the odds. That's the odds.
You got the odds. You didn't do all this.
Oh, never mind.
Yeah. Okay? And then you do the same thing for the probability of hospitalization for a female. Right? And you can get all this back. Now, like I said, in a 2x2 table, you can do all this by hand. You don't need a fancy software package to run this logistic regression. You can get the logistic regression model by hand. What's of interest, usually, from a logistic regression model that has dummy variables in it, often what's of interest is what's the difference between those two groups? So basically the difference in their intercept, right? Well, when we're in the log scale, you take the difference and then you come back to the original scale. What's the exponentiation of a difference? I didn't say that right, but do you remember this? The log of A minus the log of B. That's the log of A over B. So now when I exponentiate, I get what back? I get a ratio, A to B, right? So the exponential of log of A over B is A over B. So when I work in the log scale and I take differences, the difference in the log scale is the same thing as the log of a ratio. So when I exponentiate my results, I get a ratio, right? So if I want the ratio of the odds of males to females, this is called an odds ratio. It's the typical way of expressing the difference or the comparison between the groups in a logistic regression model. Instead of differences, we do odds ratios, right? So the odds ratio, odds for females, here we go. The odds for, let's see, males are the 0, so we'll do the odds for females over the odds for males. Right, so the odds ratio, females to males, is 0.12007 over 0.04877. Do that on your calculator.
2.461.4620.
Okay? The way to interpret that number then,
2.462 times more likely to be in a hospital for a female.
that's exactly right. You are 2.462 times more likely to be hospitalized if you're a female than if you're a male. Okay? So that's the interpretation of odds ratios. Okay? Now, one other thing to do from this before we go to SAS. Our model, where is it? There it is. Here's our model. Take the exponential of the B1. Exponentiate this number. What did you get? This number. This is B1. Take e to the B1 power.
2.4621, the same one.
2.462.
1.
Okay, so there's some round off error, but, right? So this is the exponential of B1. You could also write it as e to the B1 power. Well, that's a cool thing about logistic regression is if you exponentiate the parameter estimates for a particular x variable, it gives you the odds ratio for a 1 unit change in that variable. Oh wait, I've heard of that before. Unit change in x? That we used to call the slope in a linear regression model. Well, now it's not slope, it's odds ratio. For a 1 unit change in the x variable, the ratio of your odds of being hospitalized is e to that parameter. Right? Now you can prove that pretty easily. If my model is log odds hat equal B0 plus B1, and I'll just call it x. And let's say x is a dummy variable, so it's 0, 1. Right? Then the odds are e to the B0 plus B1x. Right? And the odds then for x equals 0 is, if x is 0, e to the b 0. The odds for x equal 1, e to the b0 plus b1x. What?
X is 1.
X is 1, so you got it.
Oh, yeah. I need that too. Right? Now, take the ratio, put the 0 on the bottom. Right? So the odds ratio, OR, is e to the b0 plus b1 over e to the b0. Be careful with the word cancel, but what's x to the third over x squared? X, right? So what is x to the 2 plus 1 over x to the 2?
1 plus
X to the 1, right? So this is x to the something plus something over x to the first something, right? you're left with e to the b1. And if you need further algebraic step in there, you can add a step. When you multiply like bases, you add exponents. So this is algebraically equivalent to e to the b0 times e to the b1, right? Over e to the b0. And now you can cancel, and you get e to the b1. So e to the b1 are the odds ratio when you go from x equals 0 to x equal 1, a 1 unit change in x. Right?
So that's always going to be for the what do you call it, non-base group.
Reference group.
Is that the reference?
The reference group has x equals 0, and it is always on the bottom of the fraction, right? So just think of it this way. The smaller value x is on the bottom. The bigger value, 1 unit increase, is in the top. So if I have a continuous x variable, not a dummy variable, like let's say I want to predict whether or not you get hospitalized based on your height. I don't think that height would have anything to do with hospitalization, but it might. Who knows? You would do the same. The interpretation would be that this is the ratio of odds of being hospitalized if you're 1 inch taller than another person, right? Your odds compared to theirs. Okay? It's a 1 unit increase in that x variable, whatever x is, whether it's a continuous variable or a categorical variable with dummy variables. Okay? All right, let's run this in SAS. Now, in order to make this show up on the camera, I'm going to run it, and then I think I'll copy and paste it into Word, and then you can zoom it out, because I don't know how to zoom inside of a SAS window. I can't figure out how to do that. But here's the syntax. It's proc logistic. For regression, you use proc reg, right? So it's proc logistic, then the name of the data like you're used to, and then this option descending. I'll show you with and without that the difference, right? But descending means we want to model the probability of a descending value of the y variable instead of ascending. The default is to ascend, so go from 0 to 1, from not hospitalized to hospitalized. I'm reversing it here, right? And then I've got it commented out, but proc logistic will allow you to put in a classification variable. So here we have a dummy variable for sex. It's numeric 0, 1. So I don't need a class statement. But suppose I had race, and I had values of white, black, Asian, and other. Something like that, and they were character strings. I could put that in as a class variable, and then it will internally do the dummy variables for each of those and fit the model. The output looks different. The interpretation is the same. Okay. But I'm going to run this. This weight statement, you won't have to deal with that. It's because I've set my data up this way, where I only have four observations in my data set instead of 2,000. If I have 2,000 and I have their sex and their hospitalization status for each individual, I would have 902 of them that had 0, 0. And then I would have 44 that had 0, 1. You see what I'm doing? Okay. So this is just a compact way of doing it, and use a weight statement. So weight each of the observations by the variable count to say there's this many like that. Okay. So I'll hit run. And like I said, I'm going to drag across this and paste it into a Word document so I can zoom it up a little bit. Does that make them bigger? easier to read. You know what I'm going to do is I'm going to set this thing up here. It'll keep pointing at it. But this is the very top. I scroll to the top of the SAS output. So let's see what it's telling us. Data set name. That you probably don't need. What the response variable is. How many levels there are of the response variable. This is dichotomous analysis. The logistic regression also works for polygamous. What does that mean? It doesn't mean you married more than one woman. That's polygamous. This is polygamous, right? So it means poly means many, right? So many levels. So it's categorical, but it's got more than 2 levels. Logistic regression, the proc logistic will handle that situation. We won't do it in this class. So then the weight variable is count. Model is binary logit. That's the default. If you want to use some other transformation other than the logit, you can do that. Right? Then number of observations read and used, and then sum of the weights, 2,000. That should be your sample size. Right? Sum of the weights. So then it says response profile. We have 0 and 1 for hospitalization, and here are the totals for those. We had 157 that were ones, and 1,843 that were zeros. So being hospitalized is fairly rare in this data set. Then it says model convergence status. Well, we don't care too much about that unless it doesn't converge, and then we got a problem. Right? So anytime in SAS or any other statistical package, when you fit maximum likelihood estimators, it's generally an iterative algorithm that the computer runs. It says, well, let's try these estimators first. Okay, now let's tweak them a little bit, make it better and better, and finally it will converge and it stops getting better. And so this is saying it converged, and the criteria was 1 times e, or times 10 to the negative 8. So it didn't change by more than that amount from one step to the next. It says, okay, I'm done. So it's just a numerical algorithm. Then we get an AIC. What is AIC? Aki-Iki's information criteria. Same one we talked about before. SC is Schwartz criteria, and it's almost always almost identical to AIC. So it's really, take your pick, it doesn't matter. So model fitting criteria. -2 log likelihood. Right? Also very closely related to those. They're just criteria for model building, so if you try a different model, you can compare that model to the one you got from this one and see which one is fitting the data better. We don't get an R-squared statistic from logistic regression. There is something called a pseudo R-squared that is sort of an attempt to get something that acts the same way, but you don't really need it. You can just go with those criteria. So here we go, fitting the model. Analysis of maximum likelihood estimates. We get parameter, degree of freedom, estimate, standard error, and then a p-value. And it comes from a chi-square approximation to this distribution. But look at the parameter estimates. They look familiar? Not quite the same, but real close. Why are they not exactly the same? Just round off error, right? If we had kept, we did this after we rounded probability to 5 decimal places, or probability to 4 decimal places, and then we kept 5 for odds. But if we had kept 20 or more, like it will internally in the computer, then we would have matched this number out to 4 decimal places. Okay? Then it gives us odds ratio. So odds ratio for sex, 2.462. That's the number we got by hand. Right? Never quote a p-value unless you know what you're testing. What are we testing with those two tests? whether they're 0 or not. Are these parameters 0? If there is absolutely no association between gender and hospitalization, what would you expect this parameter to be? 0. There'd be no increase in your log odds when you go from a male to a female. But the fact that it isn't 0 and it's statistically different than 0 tells us that there is a difference in the probability of being hospitalized for females than there is for males. They are statistically different. Okay?
Why is it a chi-square test?
The walled chi-square, when you see the walled in front of it, it's saying we're using a normal approximation of this. They do a chi-square. If you square a normal, you get a chi-square.
Right.
And if you took the square root of 24, then you'd get a z statistic. You get exactly the same p-value. I don't know why they go to chi-square, but that's the convention. But
So you don't have to?
no, as long as you have 1 degree of freedom. If you got a variable in here that has more than 1 degree of freedom, you'd have to do the chi-square. Right? But when a z squared is a chi-square with 1 degree of freedom. A chi-square with more degrees of freedom is the sum of a bunch of z's, and it doesn't work. Okay? There's some statistics down here that help you with model fit. Percent concordant, percent discordant, and then tied. So we had 25% concordant. There were 25% of the observations that the model correctly predicted, basically. And then it missed on 25, and then it was tied. Right? And tied means that... Now I got to remember how this works. Well, I'll have to look that up. I'm not remembering off the top of my head how that exactly works for tied. It's like the model. It has if the modeled probability is 50%, then it's too close to call. Like, well, I don't know whether they're going to be hospitalized or not. 50% chance. So that's a tie. So I don't remember how it all works together, but half of the people in the data set had a probability too close to 0.5, so they called it a tie. The rest of them, it got 25% of the other 50% right, and 25% wrong.
Is
So
that what you want to see?
That's what I was wondering.
You want percent concordant to be pretty high. Right? This data is not horrible, but it's not that great. Which is saying what about males and females? Yeah, it's not that big of a difference. There is a statistically significant difference, but it's not that big of a difference. Right? And if you just tell me somebody is a female, then I still say they're probably not going to be hospitalized. Because 10% of females were hospitalized, so 90% chance they're not going to be hospitalized. So it's not helping me predict all that much.
Is that like the last year, just out of curiosity?
This is 2007 data.
Okay. Okay, so it is within a year period. So like.
Yeah, it's within the year. Hospitalized within the year, that's right.
If you want to do, I know this is hypothesis, but say you want to do hospitals and hospitalization, sex, and race, you just put another dummy variable.
Yep, exactly. You can add whatever variables you want to this model. Right. We'll practice that here in a second. I want to show what happens if we use a class variable instead of a dummy variable that's 0, 1, because it changes the parameterization of the model. It gets a little bit confusing, but what we did with exponentiating the B1 doesn't work. So let's take that asterisk off of there. So now I'm telling it that sex is a class variable, which it really is, rather than a numeric variable. Right? Now if I run it, and I forgot to clear the output, but let's just do this much of it. And I'll go over to the word. Can you see what's different here?
This x is a negative, or okay about that. So it used to be positive.
Look at the intercept is different. It was
3.0.
negative 3.02 or something.
The log chi-square is way higher. Double.
Yeah. And then the sex parameter is negative 0.4504. It was 0.9 positive 0.90 something before, right? So it changed my parameter estimates. What did it do to this? Odds ratio before was 2.462. We'll take the reciprocal of 2.462. Take 1 divided by 2.462. What do you get? 0.406. So what did it do when I made it a class variable? It switched my reference group. It put the other one on the bottom, right? Which is fine. You know, interpretive wise, you just have to know what you're doing. And it tells you, because it knows it's confusing. It says sex 0 versus 1. The versus is always on the bottom. So this is 1 or zeros over 1s. When we did it as x was a continuous variable or a numeric variable, it was the smaller value always goes on the bottom. Right? So if I want to flip this one back around, then I can use the option, I can take out the option of descending. So I'll comment out this descending. Oops, I did that backwards. So I take out the descending, and these flip to positive parameter estimates, and now my odds ratio flips over the way that I want it, 2.462, right? But if I scroll up, there'll be a message that SAS is modeling the probability of I thought it would say that. There it is. Probability modeled is HOSP equals 0. Right? So if you use the descending, it says probability modeled is HOSP equal 1, which is usually the way I want it. I always I want to model the probability of when you increase in your dummy variable, go from 0 to 1. So I model a yes rather than a no. But depending on what kind of parameterization you do in the model, and I don't care that you know how the SAS is doing it internally, but basically it's setting up the parameter estimates. I don't know how to say it. It sets them up differently, but it's doing exactly the same thing. Algebraically, it's equivalent. It's just, instead of the intercept being applied to the reference group, now it's like the average of the two groups. So then each, let me scroll down. If I ask for solution, so sex 0 is now 0.45 above this one. So if I add 0.45 to that, what do you get? 3.02, our old intercept, right? So it's just changing how it defines the intercept. So then the parameter estimate, you still get to the same thing. If I do predicted values, they're under here, predicted values for males, predicted value for females, I'll get exactly the same predicted odds and predicted probabilities. It's just I'll use different numbers for them. And what SAS does is it calls one group -1 and the other group 1 instead of 0, 1. Right? So then instead of plugging in a 0 for one of them, you plug in a -1, you'll get the same predicted value back. Okay, so now I want to load up a more complicated logistic regression model. And that's this one. Okay. Let's make sure that's pointing at the right place. Oops, I forgot to hit. Did I hit run? Okay. Yeah. So I got the same 2000. It's reading it. This is basically the same data, but it's got other variables in it, so it's got a different name. But let's look at this code before I run the logistic regression. So it says set that data, but then it says if count IP equals 0, then hosp equals 0. Right? So IP stands for inpatient. So it's the count of inpatients. So if you get hospitalized, you're called an inpatient. Right? So if count IP is 0, then hosp equals 0. If count IP greater than 0, then hosp equal 1. So that count is how many times did they get hospitalized. Well, I want to collapse it into just yes or no, they got hospitalized. So that's what that first line of code is doing. Right? Then gender is 0, 1, and I want to create a sex variable. That's just to illustrate quantitative versus numeric. And then personal health status. And you can see excellence, and I'm making dummy variables, excellent health, that kind of thing. And then race, setting up dummy variables for race. Race is a character string variable, Asian, black, Native American, and then I'm making dummy variables out of those things, right? And then, so I'm going to run all that. I did run all that already. And then let's go down and just run well, I was hoping I had one without the class variable. But that's okay, I don't seem to. Let's just run this top one. And I've got some class variables for region, what region of the country, their education, and it was things like less than high school education, some college, college graduate, graduate school. And then, so let me just run it, and you'll see the output you get. So here is type 3 analysis of effects. When you use class variables, you can get these multi-degree of freedom tests. So like personal health status is a 4-degree of freedom test. What does that mean? There's 5 categories. Yeah, remember the degrees of freedom are always one less than the number of categories. So it's testing simultaneously all of the categories of personal health status. Right? And it's testing them collectively. So it's one of those partial F tests that says, oh, test beta 5, beta 6, beta 7, and beta 8, that they're all equal to 0 versus at least one of them's different. So if you use a class variable, you can get that kind of a test. Otherwise, if you put everything in as a numeric dummy variable, you get a 1-degree of freedom test for each level of personal health status. And it's comparing, is this level different than the reference level, which is whichever one you leave out. So this is easier to interpret, I think. But now look at the p-values. What do you read from those?
Most of them are water.
Okay, age. Age is not statistically significant. That's a continuous variable, but it's saying that your age does not seem to predict whether or not you get hospitalized. Doesn't that seem odd? I would think that old people get hospitalized more than young people. But yeah, maybe after controlling for all these other variables, it goes away. Who knows? And then gender's in there. We found a big difference with gender. Asian, black, native. And I put those in purposely as dummy variables rather than to put the race variable in there. So now you see 1 degree of freedom for each of those and what it's being compared to. The one that's left out. What's left out? White. Right? And since white was the biggest group, it got put as the reference group. Right? And not my choice, but it was the author's choice. But that's the typical thing, is whichever group, particularly in the United States, the white group is so much bigger than the other groups in a lot of these data sets that it makes sense to make that the reference group. Right? So, interpret that 0.68 for me. Okay? It's not significant. So interpret that for me.
If your age
Has
is
no effect on whether or not you get hospitalized.
What's that?
It has no effect on whether or not you get hospitalized.
Almost. I could say that a little better. Anybody else want to take a crack?
if your race, knowing the race does not.
No, I'm looking only at Asian here. 0.68.
If your race is Asian, it doesn't. It's not different.
Compared to what?
Compared to being white.
Compared to whites. There is not a statistically significant difference in hospitalization rate between Asians and whites. That's what that means. Right? And then black, look at that p-value. 0.997. So absolutely no difference. Native Americans, still no difference. So we didn't find any difference among any of the races from whites. And then region of the country, not significant. Education level, not significant. Let's see, I don't remember what this one is. MNH poor.
I would assume your staff, your social.
Yeah, it's probably but income's in here, but it's kind of interesting. I don't remember what any limit is either. I didn't look this one up before I ran it, but I think it's whether or not you had any limit on your health insurance, right? If you have, some health insurance policies say, well, we're going to pay, but we're going to cap you at this. Anything above that is out of your own pocket, right? So if there's any limit, hey, that was a big predictor of whether or not people got hospitalized, right? Which is sad, but it is. And then income is also a big predictor, right? Higher income people tend to be more likely to go into the hospital. But also, low income people tend to be sicker. Right? So, which way did it go? Which way is we got a significant difference, but which way did it go? Well, we got to look at parameter estimates and odds ratios to make that decision. So let's look at income. Is set up, it's high income. They're not in order because SAS alphabetizes, but high income, low income, medium income, and poor, right? So, in poor, I'm not sure. Not poor? I think it's poor. But, well, you can't tell from here what the reference group is, but let's go to odds ratios. Yeah, here they tell us. High income versus poor. So in poor must be just above poor. So poor is being left out of the previous. So now we know what the reference group was, right? So income, high income compared to poor has an odds ratio of 0.398. What is that saying?
So they're hospitalized at 0.398 every one.
What's that interpretation? Peyton, what did you say a minute ago when we had a number of 2.46?
2.46 was the odd. You were 2.46 times more likely to go to the hospital if you were a female than you were.
Okay. So what is this? 0.398 times more likely. In other words, you're only 40% as likely if you're in the high income group compared to poor group. If you take the reciprocal of that, then you can say a poor person is, what's the reciprocal of 0.4? 10/4 or 2.5? 2.5 times more likely to be hospitalized if you're poor than if you're high income. And then 0.63 for low income, 0.54 medium income. Notice there's sort of a, what we would call in the drug industry, a dose response here. These are out of order, but it's the smallest value for high income, then median income, then low income, and then in poor, just above poor, right?
So is that, so like your interpretation of that would be the poor are more likely to be hospitalized, and so you like look at, because they maybe wait before it's too late.
Or they
Yeah.
only have access to emergency
Or
Yeah. Yeah, often that's the case. Yeah. Okay, well, I ran long. I'm sorry I wasn't watching my watch. But we'll pick up more on this on Wednesday. And I'll have a homework set for you to do over logistic regression by Wednesday.
Did you post that for the project?
Maybe not yet.
I remember seeing that.
Okay.